And I'm much more an expert on extreme value theory. And Nicolas Lafont, who's a PhD student who makes a bridge between extreme value theory and machine learning. And he's a very good student. You will see his work. And mostly this work is due to Nicolas, and I think he will be on the job market in 6 months. So I will strongly advise him here. What the main motivation of this work is just that to say that suppose like you have a river network. Here it's a Danube River, and suppose you look at the 5 stations up there, like 23, 24, 25, 26, 27, and you are interested in the extremes. So what I mean by extreme is not the 90 or 95 quantile, but much more the 99 or even larger. So very much extreme value theory in terms of discharge levels. And so here we'll focus on this 5-time series. And so let's suppose we have only 2 right now. Suppose you have like the first time series, this one, and the second one is this one, y-axis. And then what you will like to do is to compute the probability that an extreme event happened here. Okay, of course, right now there is none. But you would like to extrapolate from this data set, let's say here, and see what's the probability to have blue points here. Okay, so that's basically the main goal of my talk. Okay, and if you want to do that, you can say, oh, I'm going to use machine learning techniques, and I think you are all aware of the really excellent capability of this kind of approach today, but they're not necessarily tailored for sampling multivariate extremes, because if you have a training data set which has no value of extreme in the training data set, if you want to go above the largest possible value observed in the training data set, it's a little bit more complicated. And on the other side, there is people who have been working on extreme value theory for a long time, basically starting in 1928. And so can we bridge in some sense the two together? Okay, this machine learning techniques and extreme value theory together. And already there is some people who are trying to look at what's called a GAN approach, generative adversarial network techniques, with extreme value theory. So it's fairly recent work, as you can see here, Pareto GAN, AV, extreme value GAN, and so on. And also there's people who have been working on quantile regression for extremes or extreme random forest. So all this work try to couple these two approaches. Mostly it's kind of a regression. You have X and you want to predict Y, a single Y. In our case, it's kind of different. We want to do that in a multivariate way. Okay, so we don't want to do prediction or quantile regression. What we want to do is to resample extreme value from a data set. Okay, so basically it's back to this problem at the beginning. So we want to do a generative sampling algorithm that will say, oh, what kind of value can we have here? Okay, so anyway, you can stop me anytime if you have questions. But here, so what we are going to focus on variational auto-encoders. I'm going to explain what it is. I'm going to explain what's multivariate extreme value theory, and then I will try to see how this improves the structural dependency among extremes. Okay, so I think most of those following slides maybe are not, if you are familiar with variational auto-encoder, it's okay for you, but basically I'm going to give you a very quick review. I'm not a specialist of that, but this way I look at the problem this way. I'm a statistician by training. So let's look at if I have ID data, a sample, a multivariate sample. And then if you want to speak about variational autoencoder, you could see it in basically in 2 steps. The main idea in some sense is really like you have a latent state, okay, which is a simpler version of your data set. And then what you would like to do is from this latent set I call Z, you would like to be able to draw from this probability P of Z. And then from that, given Z, if you have the right model, you would like to draw X prime from this distribution. Okay, so it's a simple sampling algorithm. But and then how do you want to parameterize your distribution, the probability of X given Z? You would like to be closer as possible to the truth that you would like to sample from. Okay, so that was these two steps in this kind of technique. First, you can view it as you start from a sample vector Z, okay, and then from that, given Z, you sample X, and then it gives you X. Okay, so that's called a decoder. And then you will like your output to be closer to the input of your algorithm. Okay, so that's the classical thing. And so, of course, you will like also to go from X to Z because you don't know Z. You will like to do the model from X to Z. It's called the encoder. Okay, so like in this framework, there is you will like to compute all the parameters of your distribution. And in general case, it's not possible, and you have to do some approximation. And one possible way of seeing this problem is to really think about here you have the decoder. So in some sense, what you want to maximize your kind of likelihood with respect to Z, and then you have a kind of a cost function. Oops, sorry. Here, Kullback-Leibler distance for the encoder, and then you will say, oh, from my approximation, I call Q, I want to be closer to my probability POs. Okay, so, but I think maybe a graph is better than that to explain this. So basically, you have this framework here. So from X, you can go to Z with the encoder, and you don't know exactly, so you have Q phi of Z given X here, which is an approximation. And then when you have Z, you will like to get back to the original symbol X, and then you have the decoder to do that. Okay, that's very classical. So it's a state-based model at some level. So now you can see that how people do that in practice. You have to impose some distribution, and if you are a statistician, the simple usually you think about some distribution. You like to speak about the normal distribution, the uniform distribution, and the exponential distribution when you do a statistical class lecture. So here, people take the Gaussian distribution, which is fantastic because you can say, oh, I have a normal distribution for my Z, my prior here. My likelihood is also a normal distribution. And then my posterior, in some sense, my approximation of my posterior, it's also a normal distribution. But the added value from machine learning is like, oh, you can view the mean and the variance of your normal distribution as neural network function, okay? And then you can deal with that. Basically, if I go back here, what's happened in practice, you replace that by you follow the mean and the standard deviation, okay? And the mean and the standard deviation are modeled with a neural network, okay? That's what people do. And it works very nicely in some sense. But by construction, it's a big but here, by construction, everything is based on the normal distribution. And because it's based on the normal distribution, except if you have an infinite mean or infinite variance and stuff like that, you cannot go very far in the tail. Because the normal distribution is basically almost like a compact function. It's not compact, but you cannot go very far in the tail. Okay, so by construction, it's very hard to go outside of the largest value. Oops. So, so basically what I'm saying is like if you have heavy tail distribution, I'm going to explain a little bit more what that means. It's difficult to generate new data which are very far away from the mean and the variance. So now step 2 of my talk, I'm going to talk about multivariate extreme value theory. And then step 3 will be to put the two together. Okay. So how many of you know about extreme value theory? 1, 2, okay. So basically, one of my ideas in math in general, but especially in extreme value theory, is to say what you would like to have, usually when you speak about allow a distribution is to have some kind of stability. Okay, so for example, if you take two normal distributions, you add them together, it's still a normal distribution. So you have stability by the sum. Okay, when you look at extreme, what you want, you don't want to sum the data. Either you want to take the max or you want to threshold them. What I mean by that is like, given that you are large, what's the distribution of being even larger? Because you're interested in the extremes, okay? Makes sense. But if you think about like the exponential distribution, it's a case. If you take an exponential distribution, if you look above a certain threshold, very high, it's still an exponential distribution, okay? This is what this graph means here. Okay, so that's true for the exponential distribution. You could think it's like, is it only true for the exponential distribution? The answer is no. So uniform distribution has the same property, for example. If you take a uniform distribution and you say, given I'm above a certain threshold, it's still a uniform distribution. And, oops. The set of all these distributions that are invariant by thresholding are called Pareto distribution. And they have this very simple form for the univariate case. Okay, so here the parameter C, it gives the tail of the distribution, if it decreases exponentially fast or not, or if it could be negative, it could be positive. And so we say it's heavy tail when the shape parameter C here is positive. Okay, but that's the only distribution that has this property. So the uniform, the exponential, the Pareto distribution, and all that have this property. So now if you want to think about going above the largest value, then the math part tells you that should be the right one, because this is the only distribution that can be an attractor in some sense. So that was for the univariate case. And if you want to draw from this distribution, it's very simple. You can take an inverse gamma distribution. So you take a gamma distribution, a draw from a gamma distribution, you take the inverse of that, and then you multiply by an exponential distribution, and this is give you a Pareto distribution. Okay, so remember that. If I take the inverse gamma distribution, and I multiply by something which is random, which is light tail, then it's again a Pareto distribution. Okay, so if you keep that in mind, you will understand after what we have done. So now I just spoke about a univariate quantity, 1D quantity, but extreme variate theory also work in the multivariate dimension. Okay, if you have 2D, 3D, like in my example at the beginning, we have 5 dimensions. We have 5 stations. Okay, so there's different way to look at multivariate extreme variate theory. One way, is, as I said before, is to look at block maxima. So you could take observation, you could take the block, and the theory tells you that if you look at this distribution, it converges to something which is well defined. Okay? That's one way to look at this. Another way to look at this is to say, again, now I'm not looking at only one variable, but a d-dimensional variable. I can do the same. For example, if I look at exceedances above a threshold. Here, for example, if I take at least, if I have 5 observations, to say the max is above Bn, and Bn is large, it means that at least one of the 5 stations has a large value. And then again, this converges to a generalized Pareto distribution. So there's a whole framework to do that. There's another representation, and I'm going to mention that now. And that's the one we are going to use. There is a representation to say, if all my variables are positive, which is the case because I'm looking at discharges, it's always positive. Then one way to look at things is to say, I'm going to use a norm, and you could take the L infinite norm or the L2 norm, but in this case, it's very convenient to take the sum. Okay, so I'm going to call R the sum of my coordinates. So if I have my 5 stations, it will be the sum of the 5 stations. Okay, and then I can renormalize the dependence part by saying it's a radial component, the angular part, I take x1, I divide by the norm of x1 plus x2 plus x5, x2, and so on and so forth. Okay, so now I have two parts. One is the intensity of the sum, and then what happened on the simplex. One way to see that is to look at what we call multi-regulating variation. So here, simply it means that what I want is to have a Pareto tail. Remember before I have minus 1 over c, so my alpha is 1 over c, but basically it said that the theory tells me that a good distribution to model multivariate extreme value theory is to say the radius here follow a Pareto tail, and then the angular component, given that my sum is large, is going to be a well-defined probability measure, and it's called the angular measure. Okay, so these look very technical at some level, but don't worry too much, because you can see in a different way. You can see it as a firework, basically. Okay, so basically, when you think about extreme value theory, at least in this case, you can see I take my space, like my 5-dimensional space, I take the sum, and then the sum gives me the intensity. So the sum is like, give me like how far I can be very detailed. And then what's happened on the simplex gives me the dependence. Okay, so this is a kind of a really simple analogy, and maybe wrong in some sense, but it's to keep in mind that if you want to do extreme value theory, one way to do it is to define the intensity in one direction and the dependent on the sphere, the simplex. And the two, when the radius become large, are become independent. So that's what the math probably tells us. Okay, so what does that mean in practice? In practice, it means that I have the radius r, my sum, and I have the angular measure. Okay, I have these two components. Okay, and then from that, if I want to sample, because remember from the start we want to sample stuff. Okay, we want to draw stuff. So how we can sample x now? You can draw a radius r prime, let's say, from a Pareto distribution, let's say, and then given the radius, I can deal with the angular part, and then the step number 3 is very simple. I just remultiply the two together. So now I have a sampling algorithm, okay, for extreme value. Good. Oops. So now we are going to the last part of my talk in some sense. At the beginning, I mentioned variational auto-encoders. I mentioned in the last part multivariate extreme value theory. And now I would like to put them together. Okay. So so remember, I have my 3-step before. So what I did in subsets is just to add this word. Now we are using a variational auto-encoder to deal with the radius. We are going to use a variational auto-encoder to deal with the angular measure, and then we put back everything together. Okay, so in subset it's not that that complex. But the scheme is a little bit more complicated now because I have two parts now. I have my Z, my hidden space. Before it was only Z in some sense. Now I have Z for the strength, the intensity, the radius, okay, which is here. And then I can draw something from there. And then given that, I can draw an angle, give us this angle. And this is going to give me the angular part. Okay, and then I'm going to give me the sample x. Okay, so and of course I have to do the same for the decoding part here. So I take x, I do the radial and the angular measure, and then I do the classical. Okay. So let's look in more detail about this part. Okay, so here it's just the radius, the 1D radius, give me the intensity and the strength of the event. Okay, so to do that, I need to fix a model. And before, remember before what people did, they put a Gaussian distribution. And we don't want to do that. We don't want to use a Gaussian distribution. Okay. So what we want to do, we want to say, oh, the prior distribution, it's an inverse gamma, because we know it's a good distribution, the inverse gamma, because the inverse gamma multiplied by a random variable with finite moments will give me a Pareto. And that will be in compliance with extreme variate theory at the univariate variable. So in some sense, that's what we did here. So the prior is going to be like this. It's an inverse gamma. Z given the radius is also going to be an inverse gamma because it's kind of a multiplicative model, or given the radius is going to be a gamma. Okay. The main difference, before we had the Gaussian distribution, and then we don't have the Gaussian distribution. And so because we don't have the Gaussian distribution, we don't have the mean and the standard deviation to model, we have the parameters of the inverse gamma to model. Okay. So a natural way to deal with that is to set neural network on the parameter of the inverse gamma distribution. So basically, we can do that. That's what we have done here. Let's see. But in terms of, remember at the beginning, in terms of the estimation, I used the so-called elbow approximation. And basically, just to remind you what it is, elbow was two parts. This part is a Kullback-Leibler divergence here, and part here it's a likelihood part. And so we want to maximize the two, in some sense, together. One is to say the model fit well, and the model is to penalize a little bit in terms of the complexity of the state space model Z, in some sense. So, but because we impose, an inverse gamma, the distance of the Kullback-Leibler here can be expressed in terms of the parameters here. So we have an explicit form, in some sense, like before, we had an explicit form for the Gaussian random variable. Here, we have explicit form from the inverse gamma. Of course, alpha, for example, alpha phi of R, alpha phi, it's a function, and this function is going to be modeled with a neural network. Okay. So of course, we have to put some constraint on the neural network to adapt to the constraint we have. We want to have every tail index distribution. And one big difference with what usually people do in extreme variate theory, usually people set a high threshold and they model above the high threshold. Here, we don't take this value. We don't have a threshold selection step because we define extreme as distribution as an inverse gamma multiplied by any random variable which has finite moments. So we don't have to deal with the threshold selection. But I will come back on that later on if people want to. And as I say, if you look at fireworks, there is two parts. There is the strength of the event and after what's happened on the sphere. Okay, so to deal with the sphere, which is this part here, it's a theta, the angular measure. Here we do, because this is not a univariate distribution, it's a multivariate. So we take the normal distribution and then we project the normal distribution into the sphere, I mean the simplex in some sense. And then we do the update also this way. Okay. So now maybe I have 5 more minutes or 2?
4.
4. Okay, great. So I'm just going to finish with 2 examples. One is from a simulation and one is from the data set I gave you at the beginning. So basically what you have to keep in mind is the training data set here is 250 and this is 10,000. So the test, and here it's 750 and 18,000. So it's pretty small training data set and large test data set because we want to look at extremes. Oops. So let's go back to my original problem here. And so if I take the standard VA approach, so I use off-the-shelf technique. So when I look at the blue point here, the blue point and from the data set I have. Okay. And this is generated from the classical Gaussian-based variational encoder. So in some sense, you can see The orange point are not capable with the classical approach to deal with the blue point. Okay? Now, if I look at the approach we propose here now, the one which is called extreme variational auto-encoders, now we are able, for this data set, to have points in the who are closer to the training the test data set. Another way to see that is like this is for the Danube River. I'm going to be fast on this. If I want to look at the event, station 23, it's above the high threshold, station 24, station 25. In my training data set, I have 0 data. It's in the test data set, it represents 0.5%. 0.5%. Now I want to fill up this table, okay? And you can see if I increase the size, no, I don't look at the station 23 and 24, 25, but I look at 23, 25, 26, 27 together, then there's very few data sets in my test set and 0 in my training. So what's happened here, if we look at our approach in some sense, we get at least positive number. If I do the standard VAR, it's pretty bad. It's always 0, basically. And if I look at the parallelogram, it's little smaller than our approach. So this is just a real data set, but it shows you basically that with standard approach, it's difficult to get anything extremes. And with our approach, we are closer. In terms of the dependence on the angular measure, you can see that with a standard approach, like the parallelogram here, we get this kind of cloud, but we should get this one, and our approach gives us this one. So in some sense, this represents the dependence. It's kind of complicated graph, but basically this shows that the dependence structure among extremes is much more well captured with our approach than with the classical parallelogram. So I'm going to conclude very quickly. So we have a paper on arXiv, it has been submitted, so you can look at that. But basically what I would try to do is to tell you that maybe by combining multivariate extreme value theory and variational encoders together, you can improve variational encoder to capture what's happened in the extremes. And it's feasible to do that by using inverse gamma distribution in the elbow metric cost in some sense. Of course, there is a lot of things to deal with that. This kind of approach could be applied to other problems, like in assimilation data or forecasting extreme or so forth. In terms of theoretical work, we could go a little further. And here we look at small data set. It was 5-dimensional in some sense. To scale up is maybe a little bit hard. And also here our data set where we took stations were very close to each other. So they were a strong dependence. When there's a weak dependence, it would be a little more difficult. So I think I'm going to stop here. And feel free to ask questions.
Yeah, thanks. Yeah, I have a couple of questions for Phillipe. Yeah.
Yeah, thanks for the really interesting talk. If I understood your setup correctly, it seems you're doing like an extrapolation problem. There's basically nothing over there.
Yeah.
And so it seems to me then you're really relying very heavily, I guess, on the implicit bias in the model validation, but that could have a huge effect on the output. I was wondering if you could comment on some of the robustness or anything like that of your method.
Sure, for online, but basically, what's the robustness of a method for extrapolation, essentially?
Yeah. So basically, it's always, I would say, dangerous to extrapolate beyond the range of the training data set you have, obviously. But this is not a problem specific to machine learning. And in some sense, I can give you an example where you have, let's say you have 30 years of data or rainfall, and you have to set the return level for 100 years. So how you do that? And people in the community, at least some of the people in the community, have said, we need a model to do that. Okay, and to do that, what they say, we are going to base our robustness in some sense with respect to the probability theory. And the probability theory tells us that if you want to go beyond the range of the largest observation, you can rely on extreme value theory under some condition. Okay, and so in terms of parameterization, I rely on this. Okay, but of course, if the condition to apply extreme value theory are not satisfied, this will be not very robust. So in some sense, but it's a bit like the central limit theorem. If you want to model averages, you will say I'm going to have a normal distribution. Well, if you take the max of a sample, if you want to model that, the theory tells you the only possible distribution for the max, which is non-degenerate, it's an extreme value distribution. So you are right, and what I didn't talk about also, it's important to have confidence intervals on this kind of result too.